You're all set. It's not everything. See. Uh, Here. And habitat. It's not sure. Oh, search out. Oh.
You going for coffee?
I already have. Okay. So the other car and so.
Yes,
It's
I seen.
I think the. Out with.
Lunch.
Yeah, the 30.
Yeah, once.
Yeah. Good idea. Yeah. Oh, thanks for helping.
No problem. Coffee from whoever wants. If you need anything, I'll turn it on. Unless it's me. But, you know.
Okay, and you stop the words.
Yeah, I'll come back and clean it up.
Right.
And I'm also gonna break for lunch for them.
That's good. Okay, thank you so much.
You're welcome.
Sorry. Yes, you can kind of monitor the rule. From Carl and Stefan is actually. Yeah, I will monitor the chat. If there's any questions. Good. Yep. Let's maybe wait just 2-3 minutes to get started. Sounds good. Yeah, okay. Is here? I knew you did. Yeah, when I met with Carl yesterday, I was gonna bring up the stuff you're looking into. Got there, or the So, I believe I'm grader. And for others.
Okay.
I need to learn that.
Nice. There's some of them too. Yes.
Yeah, so if you mind just having a short conversation afterwards. You're good. Yeah,
Sounds good.
yeah. All right, let's get started. So it's a great pleasure for us to have Professor Kyle Wassgren here, giving us a talk about modeling the damage of corn kernel during processing. So Kyle got his educations at the University of Illinois and also Caltech, and then he became a professor at Purdue University in mechanical engineering and also in industrial and physical pharmacy. So as this suggests, Kyle is an expert in everything related to powders and granular materials, and he's an important part for Purdue's research center for particulate products and processes. And on top of that, Kyle received several prestigious awards for teaching. So I think that's more reason for us to look forward to the presentation. So yeah, please go ahead.
Thank you. So first of all, thank you for the invitations to come here. I really appreciate Hanyi's efforts on putting this all together, especially for you coming out on kind of a crummy day, and yesterday was sort of a crummy day as well. So I appreciate you being here. So I was going to talk about a very specific topic. I guess maybe I'll back up a bit and mention that. So I've been studying particulate materials ever since I was a graduate student. So in a wide variety of applications and different systems and such. Now, at the beginning of my career, I did a lot of fundamental work, more kind of physics-oriented type of work, and then over time, I drifted a little bit more toward applied topics, and toward this kind of latter half of my career, maybe over the last 10, 15 years, it's been a combination of applied and fundamental, but I really enjoy the applied side. And the reason for that is seeing what the problems people are having, trying to help people solve those problems, I think is pretty interesting. And seeing the research applied in practice, I find to be very satisfying. So I'm going to talk about one of those very applied projects today, and specifically using DEM. I think many of you know what DEM is, so that helps a bit. But using DEM to predict corn kernel damage, and specifically during harvest. So over the last 25 plus years, I've lived in Indiana. I grew up in the Midwest in Illinois. And I never really did any sort of agricultural related research until about 5 years ago. Seems like I should have done it earlier, being in Indiana for so long with all the corn and soybeans around us. But a colleague of mine over in ag and bioengineering got me involved in this project. There was a company. So the colleague of mine is Kingsley Ambrose. So by the way, what I'm going to present today is really the work of a lot of people. Kingsley Ambrose is my colleague in ag and bioengineering. Most of the work you see here is by Jung-Poo Chen. He was a PhD student that we co-advised. And then there'll be bits of work by some new PhD students, Zimeng Zhu, Johnson, Adegboyega, and then Eric and Ashu. Those are sponsors from CNH Industrial. So the CNH Industrial makes combine harvesters and various agricultural equipment. And so they approached Kingsley. Kingsley got me involved, but they were concerned about damage to grain during harvesting. And it seemed like a really good application of discrete element modeling, because DEM, we model the individual movement of particles and such. Most of the prior DEM applications I dealt with really fine powders, really like small particles on the order of maybe 100 microns or smaller in size. It's hard to model those particles one-to-one for those applications. But corn kernels, they're boulders by comparison. They're really big, right? Roughly on the size of a 1 centimeter in diameter. So they're really well suited for DEM model. So this seemed like a pretty good project for that. So let me go ahead and motivate the work. So first of all, cereal grains are arguably the most important food source for people and livestock. So cereal grains are grains that come from basically grasses. So examples of that would be like corn, wheat, rice, soybeans, and there are others. But really, the enormous amounts of these cereal grains are harvested every year. You can see here, 1,100, just over 1,100 metric tons of corn are harvested each year. That's a huge number, and it's hard to put it into perspective. I asked ChatGPT to see if it could give me a better way to understand that number, and it told me it was equivalent to about 11 million, the weight of 11 million blue whales, which I don't think is any more helpful. Still a huge number, but it's just a vast quantity of material that's being harvested, right? And when it's being harvested, a lot of it gets damaged. Okay, so you can see that about just under 1% is fragmented corn. So like the corn kernels are just completely broken in half. About 8% are chipped or with external cracks. So just a little bit of the edge is broken off. I actually can show you a picture of that. So the picture on the bottom left is this external damage, chipped or with external cracks. What you're seeing here is a dye. It's a kind of a dye that reacts with starch, the exposed starch of the corn kernel. So everywhere you see sort of this blue color in this image, that's where there's some exposure to the atmosphere or to the dye. So a lot of it gets chipped or with external cracks, and then you have internal stress cracks at about 5% of that. And that's shown here in this image. It's a little hard to see, but the picture here is backlit, and you see a change in color where these red lines sort of encircle it. That's an internal stress crack. Over here, this is more of an XRCT image, and you see these kind of voids inside here. Those are also internal cracks. When you get these internal cracks, so it's about 15% of the material gets damaged. And when you get this kind of damage, it degrades the value of the corn. So it affects the price that the farmer will get for that material, so they find it undesirable. And then it opens up the corn to degradation, so you can get microbial damage in the corn. It gets inside there, causes some damage. And it can also affect water absorption with the kernels, and that affects downstream processing as well. So it's very undesirable to have these cracks that form in the corn. So we want to try to avoid that. Now, the things that cause this kind of damage, and there are several sources. So one is drying. So when you dry the material, the transport of moisture from inside the kernel to the outside, to be evaporated away, it can cause damage to the kernels. There can be some infestation, microbial damage that can occur. But another source of damage is mechanical damage. So as you're collecting that material during harvest, like in a combine harvester, these are multi-million-dollar devices. They're a dream for mechanical engineers. All kinds of moving parts and conveyor belts and spinning blades and things like that. But they impact and compress the kernels, and it can cause some damage during that harvesting process. And then once you have the material and you're handling it later, you have all these various kinds of conveyors that can cause some additional damage, like little kind of drag or flight conveyors, bucket elevators, material just free falling onto surfaces. So a lot of places where material can be compressed and impact and possibly wear. So these are the kinds of things that we're interested in studying here, and specifically parts inside a combine harvester. A lot of some of these applications actually occur inside these things. So we wanted to study this problem. We made use of the discrete element method to do this. It's very well suited for this kind of application. I think many of you know what DEM is all about. Does anyone here not know what DEM is? Okay, nobody's going to speak up if they don't know. But so I won't really spend a lot of time on this, but it's a pretty straightforward modeling method, just in terms of the kind of general approach. We model the movement of individual particles. The way we do that is we find the loads acting on each and every particle. We use Newton's second law basically to determine the accelerations, both translational and rotational, on those particles, integrate that in time. We make whatever predictions we're interested in within the simulation, and then just repeat that process over and over again for as many particles as we can, as fast as we can. So in concept, it's really relatively straightforward. There are challenges, though. A big challenge is getting accurate models. And when I say accurate enough for your application. A lot of people don't keep that in mind, but when you develop models, you really want a model that does something well enough for what you're interested in. It doesn't have to do everything for everybody. Just the model for your purposes and what's considered accurate enough for your purpose. Okay, so developing those models, and that can be like modeling the particle shape, the size distribution, for example, the forces involved, contact forces, whatever it is. All those things are embedded in these steps. And then perform this as quickly as possible for as many particles as you can, typically. Current state-of-the-art DEM simulations that people use in practice in industry might go up to 1 million particles, but it's typically more like tens of thousands of particles to hundreds of thousands of particles. In academia, you can get the bigger numbers, but generally it just takes a long time to run those simulations, so they tend to start with smaller numbers of particles. I used to maintain my own DEM code. I gave that up a number of years ago because it became hard to keep that code maintained with so many different students contributing to it, and they all had their own programming style, and I had to try to smooth it all out to make it more uniform. That was a headache. Training new students on using the code was kind of a headache, and simply I just couldn't keep up with all of the features that were being developed commercially. It was just a small group of us versus a team of developers who are getting paid high salaries at a company. So we just started using commercial codes, and the two that we use quite a bit are Rocky and EDEM. The other, actually, probably the biggest driver for using the commercial code is our sponsors. When we do technology transfer, our sponsors don't want our inbuilt, home-built code. They want to use something they can use internally. And so those are the two most common commercial codes. There are other free codes that are out there and such, but these are pretty straightforward to use. And they have a programming interface that you can make use of. We make use of it to do some of the things we want to do. So there are pros and cons. So anyway, that's the software that we're using. And then I'll talk in the next several slides about the models that we use before we start getting into the damage modeling aspects. So the first thing to consider is what kind of particles are you going to use? We're interested in modeling corn kernels, so not spheres. So we can easily measure the general size and mass of corn kernels. Moisture content is another thing that we measure. It turns out when you're dealing with biological types of materials, moisture content is very, very important. It affects all the properties, the mechanical properties of the particles and such, so you need to know that. But to get the shape and size, we just simply imaged a bunch of corn kernels. We used an XRCT, just an X-ray computer tomography, just made a nice outline of the kernels, so you could get many kernels measured that way and then get different shapes and sizes. We tried doing some just 3D scanning of kernels. We didn't really have much luck with that, just trying to image the surfaces. They were too reflective. The pericarp, which is just the surface of the kernel, was pretty reflective, and so we got really bad images with just 3D scan, normal 3D scanning. We tried spray painting it and all this kind of stuff, and it just didn't work. This worked pretty well. And then to represent that size, that shape, we took a couple of approaches. One was a very common bonded sphere kind of approach. You can see here we've got like two spheres stuck together meant to represent that shape. And then here's something more like, I can't remember how many this is, maybe 10 spheres to represent that shape. There's commercial software you can use to get that kind of shape representation. So we tried different bonded sphere models. And then to kind of zero in on which set of shapes we wanted, we actually just looked at the error in the volume of, so we know the volume of the actual kernels, and then we looked at the volume, the envelope volume of the bonded spheres, and we tried to keep that more or less the same. And then also the shape of the sphere was kind of set by the shape of the kernel. But here's an example of looking at the volume error, that's that black line, the error between the represented shapes and the actual volume as a function of the number of spheres. And then this kind of yellow orange line is called the EIT error. It's basically just where the mass is distributed in the particles to try to get a similar moments of inertia for the particles and such. And we found that, 4 to 5 spheres seems to minimize the error. We could go to a larger number of spheres, but it takes more computational effort. So this is an engineering trade-off, right? We do this all the time when you develop models. How complex do you want it to be? What restrictions do you have? Speed is a restriction. So we don't want to go out to, 100 different spheres. It just would take too long to model big systems of those. So 4 to 5 spheres seem to be a pretty good compromise on that. Then I'll talk more about the effects of shape in the models in a little bit.
Do you ever couple that to CFD?
So you can, yes.
I know naively just applying drag to each particle is a very simplified assumption.
Yeah.
I don't know if any better ways to do it.
So actually, this was EDEM, this bonded spheres, and they couple with the CFD code. It's the company's Altair, I think.
Yeah, I know this guy.
Yeah. So, and I don't know how they certainly use just drag coefficient models for individual spheres. I don't know what they do for bonded spheres, whether they use an envelope, spherical volume, or some correction due to shape, because there are drag coefficients based on sphericity and size. So empirical kinds of correlations. But I don't know if they do that.
If you're using bonded spheres to recreate that shape,
Yeah.
Why not just use the same shape? And
So to use that shape.
yeah.
So the issue really comes down to contact detection between particles. So when two spheres come into contact, it's very easy to determine that, right? Just the sum of the radii is less than the distance separating the particles. But when you have two irregular shapes, how do you know when these are in contact? That's a much more challenging and time-consuming problem. So the bonded sphere approach was a compromise to give you some more irregular shapes, but retaining the contact detection benefits of spheres. So it was maybe not the best
use the sign
representation.
distance level set, so you have any shape you want.
Yeah.
The problem is, when you look at the roughness and the curvature on there, to get that right, to do the detection right, it's very expensive.
It is, yeah. So that's one approach. So it's a compromise between fidelity of the shape and computational efficiency. But there is another approach. This is coming out of Rocky DEM. They use a lot of polyhedral shapes. And so you can see some examples here. And then you have the question of how many facets do you use? So we did the same kind of thing. We checked the volume with different numbers of facets. And we said, well, about 300 facets seems to give us 1% error in the volume. That seems pretty good. So in the simulations, we end up using, I think it's on the order of 10 different representative shapes, just randomly sampled from all the images we made, and then use those in the simulation. So we had some variability in shape and size, not as much as in real life, but at least we had some range. All right. So then the next modeling choice is really how do you model the contact forces between particles. So again, many of you know about DEM. We don't model any sort of real geometric deformation. Particles come into contact. Instead, we let them overlap a little bit, and we use that overlap to determine contact forces. So, normal contact force might be a damped kind of spring with various complexity. And then in the tangential direction, you can have a damped spring with some sort of frictional sliding element. Very, very common way to model. And here, and then as far as the details of that, again, there are many different force models available in the literature, but we just stuck with kind of a standard model. We used a damped, nonlinearly damped Hertzian spring in the normal contact direction, and this Mindlin-Deresiewicz kind of tangential force model with a damped spring and a sliding friction element. These are almost default models used in a lot of commercial DEM code. I don't think they're the best contact model out there. They have some deficiencies. I think they became default values because they were relatively easy to code, didn't require keeping history of contact. So some better force models actually keep the history of the contact. This does not do that, so it's a little easier to implement computationally. And so I had a former PhD student who went to work for one of these software developers, and he was kind of surprised at the lack of physics knowledge a lot of programmers had. And so I don't think they were implementing the best models. Nevertheless, it's a default model, and I think it has some impact on what we observe later, but in some cases it doesn't. But I'll talk more about that later. The models drive the parameters that you need to measure to characterize the system. So in these models, you have a contact stiffness in the normal direction that involves an elastic modulus. The E star here also involves a Poisson's ratio. Measure of the geometry of the contact. This just comes from our shape representation, so we already have that. That's an effective shear modulus, but that comes from the Poisson's ratio and elastic modulus. And then you have a coefficient of restitution in here, which is a measure of the energy dissipation that goes into the model. So we need, and then masses, which we already know. So these are the parameters you need to calibrate or measure to use in your model to get some more accurate representation of what you're actually dealing with. So I'll spend some time talking about how we got those. They're kind of interesting because we're dealing with biological materials that have irregular shapes. And so it can be challenging to get some of these parameters. So first, let me talk about contact stiffness. And again, if you know something about DEM, you know contact stiffness really affects the speed of your simulation. You can sort of get this idea here from just a simple spring mass system. And you look at like this mass hits the surface and rebounds. So if you look at the acceleration or the force acting on that particle, it'll increase, have its maximum overlap, and then separate right there. So there's a time of the contact, and that time of the contact is proportional to the square root of the stiffness and mass of the contact. So if you have, actually it's flipped upside down from that. That should be upside down, mass over the stiffness. So if you're dealing with small masses and large stiffnesses, you have short contact times. And your explicit time integration algorithm is going to be a fraction of this contact duration, right? You want to integrate under this curve. Since this is the acceleration, you want to be able to integrate that to get the velocity and integrate that to get position. So you need to make sure you have a fairly small integration time step so you have an accurate integration. So basically what you need to do, again, this should be flipped upside down, or what you want to avoid is you want to have, you don't want to have very stiff contacts. Because if you have stiff contacts, the simulations take a long period of time. So you'll see a lot of people will just artificially choose stiffnesses that are really soft to make their simulations run fast. And that's actually pretty acceptable. If you do parametric studies of many systems, unless you make the particles super soft, it really has very little impact on the simulations. But in some cases it is important. And I'll talk more about that a little bit later. So we tried various methods for getting that contact stiffness for corn kernels. First of all, there's some work out there, and we tried it as well, to use just a spherical indenter. You just take a corn kernel one at a time, set it on a platen, indent the surface a little bit, and then look at the force displacement curves, and you can get a measure for the elastic modulus. So we tried that. Very tedious, and not great, actually, because these are heterogeneously, distributed materials, right? It's biological. So you have the germ on one part of it, you've got the pericarp. Your elastic modulus varies over the surface. And we can't really account for that in the simulations, that variability. So we abandoned that relatively quickly. Instead, we
using a multi-sphere approach, you could assign different properties to each particle.
If it was your own code, you could do that sort of thing.
Yeah.
But then there comes these questions of trade-off. So you spend a lot of time getting that part just right, but your shape is super bumpy.
Yeah.
Right, with those spheres. So is it worthwhile to spend a lot of time increasing the accuracy of one little part when the rest is really pretty approximate?
But it's interesting if you're choosing to do multi-sphere anyway.
Yeah, so that you could do that.
Then you could assign different properties, which is I hadn't thought about before, but
you could certainly do that. I don't think that
then allows you to do not just shape but heterogeneous DEMs.
Absolutely. Again, you probably do that in code, not in commercial code. But yeah.
The other thing to consider, this is Carl up in Midland. The other thing to consider is the fact that the corn kernels are across an individual cob are not uniform. You have a lot that are sort of, if you looked at them in cross section, rectangular in shape. But as you get to the tapered end of the cob, you have what is in the industry are called rounds, and you have a lot of rounds. So there's more non-homogeneity in particle shape than we give credit in an ear of corn.
Yeah, that's exactly right. Yeah, if you just take a look at an ear of corn, huge variation in size and shape as you go from the tip or the base to the middle. We tended to, when we did the experiments, we stuck with the material more in the middle of the cup rather than at the ends, to try to make it a little bit more homogeneous and a little bit easier to work with. So the two ways that we used to characterize stiffness rather than the spherical indenter way was one was just a calibration approach. We just took an individual corn kernels. This was actually seed corn, so it looks a little bit different than yellow dent corn. Seed corn is used for planting corn. But anyway, between two flat platens, we would squeeze it a little bit experimentally, look at the force displacement curve. So that you can see here, force displacement, that's the black line, was just one. This is the median of many, like something like 100 different trials. The band here is just a plus or minus one standard deviation from those. And then we simulated the same thing with their different shapes and then varied the elastic modulus until they matched. So that's the different curves here are varying elastic moduli values. So something on the order of about 160 megapascals for seed corn seemed to work pretty well. So it's a calibration process rather than a measurement process because the profile you get here depends on the shape that you use. So we just wanted to calibrate a stiffness for the shapes that we're dealing with.
So for one shape, do you test different orientations? Because
No,
but for the schematic you're drawing, it seems like the concavity makes your test for like a 3 points.
yeah. So
landing.
it's a kind of a simplified drawing, but with yellow dent corn, for example, there's usually a dent in there, and that was always face down. That follows a standard that's used for this kind of test. This kind of compression test is not something new. I mean, it's a standard that's used. If you did some other orientation, it can be unstable. You can flip around while you're compressing it.
So in able to compress it, the core always falls to just like
there's a stable sort of position for it. It's certainly an approximation, right? Depending on how you squeeze it, but we can't really account for that variation in the model anyway. And again, the trade-off with speed and fidelity, you got to make some decision. So we stuck with that approach. That's one approach. And I mentioned this is seed corn because we also did yellow dent corn and that behaved a little differently. So I'll show you an example for what we did for that. Here we did another calibration approach, but it was a bulk compression test. We just took the real corn, multiple kernels in a cylinder, and then compressed the bulk and looked at the we did kind of a force displacement curve for that, and then we got a bulk stiffness from that measurement. And then we simulated the same thing, varied the elastic moduli values until we got something that matched pretty well. So the red dot dash line here is the experimental mean. The dashed blue lines are 95% confidence intervals. And then the symbols in here were different simulations that we did. And we found that something like about 220 megapascals for yellow dent corn seemed to work pretty well at matching the experimental work. So this is a calibration. It's not a direct measurement of elastic modulus. It's a calibration for our size and shape of kernels. I should also mention that we measured the friction coefficient in here beforehand and used the measured friction coefficient. So this is a calibration for those conditions to give us a matching stiffness.
Do you use any damping?
Yes. So I'll talk about that in a moment as well. The damping doesn't play as much of a role here because this is just a quasi-static kind of system. Friction is more important there. One interesting thing about this is if you look at the force displacement curves for the bulk material, the blue line here is experimental data, and of course you get some hysteresis due to frictional dissipation and such in the system. And you actually, to give you a little more detail, when you compress it, you have to do it multiple times before you actually make your measurement, because the first few compression cycles involves rearrangement of the particles. It's kind of what I was talking with you about. The particles rearrange and then they get into more stable positions, and then you get very repeatable compression cycles. But until they rearrange and become stable, then it varies all over the place. But during so the simulations modeled that pretty well, but the unloading part, the simulations didn't do very well at all. And we were kind of puzzled about that. We didn't really investigate it much further, but I actually suspect it could be, something to do with the friction coefficient involved, but we measured that more or less directly. So we had some doubts about that. Maybe the shape plays a role, but I suspect what ended up happening is we actually could produce some micro cracks internal to the corn kernels when we were doing this experiment. And so that dissipated quite a bit of energy during that compression process. Oh, and then the Poisson's ratio, we didn't really have a good way to measure that. So we just used a literature value. Frankly, it doesn't make that much of a difference because you never have the Poisson's ratio by itself in the simulations. It's always embedded with the elastic modulus as an effective elastic modulus. So when we did the calibration, it actually was calibrating the effective elastic modulus, which embedded the Poisson's ratio. So let me talk a bit about the friction coefficient measurements now. So now we have the shape, size, elastic, contact stiffness. I'm going to talk about friction and coefficient of restitution. Those are the remaining two parameters. So if you look through the literature, there are lots of different ways people have proposed for measuring friction coefficients. Many of them are bulk level tests. The problem with what I've seen in the literature for getting friction coefficients for grain is they incorporate some of the shape effects as well. So that you maybe have a bunch of corn kernels glued to a surface, and then you have another surface with corn kernels, and then you kind of tilt it until it slides, getting a friction coefficient for that. There's some shape effects in there rather than just the friction coefficient by itself. So we actually, I have a colleague who does a lot of tribology related work, and he has this pin on disc tribometer that I thought would be kind of a neat thing to try to get individual friction coefficients between a corn kernel and a surface and between two corn kernels. So the way this works, it's a little tough to see. There's a vertical component here. It's a sample holder, and we have a little 3D printed holder that we glued a corn kernel to. And this measures the vertical displacement and vertical load. And then on the bottom, there's this disc, and you can mount whatever surface material you're interested in here, or actually glue another corn kernel onto that bottom. And that rotates, so it kind of reciprocates, it rotates, and you can measure the displacement torque on that. It's a very sensitive device. And so we did two kinds of tests, one with a corn kernel and the surface, steel, basically. We also did acrylic surfaces, and then two corn kernels themselves. And this is the kind of data you get. So the left-hand side is the measured coefficient of restitution from the normal and tangential loads versus time, which is effectively displacement. So it's oscillatory. And you get these kind of profiles where you get like a static friction coefficient, and then a dynamic value, and then it changes direction, and it repeats, it goes back and forth. And so actually the data here is for wheat and acrylic, but we did the same kind of test for corn and steel. Looks very similar, I just didn't have a picture of it.
Is there a velocity dependence?
We didn't check that. These are all pretty slow velocities, but we couldn't, the machine had some limitations in how fast you could do those oscillations, so we did not check that. I was a little concerned also because the shape of the corn kernel, at least for kernel testing, they're not flat surfaces. So what happens as one kernel goes over the other, the vertical holder goes up and down. And so we took that into account for the kernel friction coefficient. So you can account, knowing the vertical and tangential displacement, you can get the local slope and then find out what the component of the friction coefficient would be for that. So we included that. If you went too fast, you might get some inertia that would skip it up and bounce. So we tried to keep it relatively slow. But we could get some friction coefficient measurements that were pretty reasonable. This is surprisingly low for the kernel, but if you ever dealt with corn kernels, they're pretty slippery surfaces. The pericarps are pretty smooth. So that gave us some friction coefficient values. So the remaining parameter that we needed to obtain was coefficient of restitution. Now, the standard approach that a lot of people take or think about with in physics with coefficient of restitution is, you drop a sphere, it bounces, you measure the height you dropped it from, the rebound height, and from that ratio, you can get the coefficient of restitution. And that works great as long as that sphere bounces exactly down and straight back up vertically, no rotation, doesn't bounce horizontal. But you can't do that kind of test with a corn kernel. If you drop it, it'll hit and then go fly off to the side and spin. So some of the energy doesn't just go into the vertical rebound, it goes into some translational movement as well as some rotational elements. So many people in the literature just use the rebound height and make a coefficient of restitution out of that. It's just not right. So we couldn't think of a good way to actually measure it directly, so we calibrated the value. And the way we did that, like for a kernel surface interaction, was this really kind of crude, simple experiment where we would drop individual corn kernels onto a boundary surface and they would bounce and land into a bin. We did this, so we do that experimentally. And then we do in our simulations using our contact stiffness, our shape, and our friction coefficient. So then we would calibrate our coefficient of restitution for those conditions. Okay. And then we repeated this with different coefficient of restitution values until we got a good match with the experiments. And that's what you see here. This is the cumulative frequency of the number of kernels in the bins. So, just the cumulative number as you work your way outward. And that's the bin number. And then the dashed lines are the experimental values for corn and wheat against steel. And then the simulation values that had the best match are shown on top. So you can get a calibrated coefficient of restitution for those irregular shapes. Tried the same thing with, instead of a flat surface, we glued some corn kernels and tried bouncing those, but we got terrible results for that because of again, they're irregular shapes. So we ended up for that using again, another literature value where they made the kernel coefficient of restitution measurements using a double pendulum device. Basically, it had one kernel on a pendulum here, another kernel on a pendulum there, release this, it impacts, and then you look at the rebounds, and you can get the coefficient of restitution from that. I still don't think that's a great measurement because, again, when those kernels hit, they're going to twist and maybe want to kind of move laterally, but that energy doesn't go into the change in potential energy. Some of it goes into the pendulum strings, kind of twists it and such, and you don't capture that in that measurement. So I don't think this is the best measurement, but it's the project, our sponsors weren't paying us to just find the coefficient of restitution. They needed us to keep moving on. So we made a compromise and decided, okay, we're going to use that value. It's the best we can do at this time. And we'll stick to that and move forward. Yeah.
Are there other sort of more like dynamic techniques where you're looking at more number of kernels that are flowing through to them back like?
So there are other calibration techniques, which we also try to vibrated bed. Mm-hmm. With the logic being, if you vibrate the particles, they'll expand more if they have a higher coefficient of restitution. We found that the simulation results, we started with simulations first before we built the experiment. And we found that it was pretty insensitive. Like the measured height, there was so much uncertainty that you just couldn't really calibrate it well. But it's potential that there are some other calibration methods for that. Yeah.
So for finding the coefficient of friction, would you be able to do the same experiment if you have spherical particles too?
You could do the same thing with spherical particles. You probably wouldn't want to displace it laterally too far, but you could do the same thing. Yeah.
Is there a size limit for some of these measurements?
Yes.
Okay.
Again, we're fortunate we're dealing with big particles, but I can't imagine a 50 micron particle, right? I mean, how would you do that? In those cases, it's really a calibration of many particles simultaneously, and frankly, there aren't good methods for it. But we're in a little bit better position since we have larger particles here. I will say the coefficient of restitution between particles does turn out to be important. For some compression damage, it's not that important. For impact damage, actually the boundary particle coefficient restitution turns out to be pretty important. But I'll talk about that a little bit later. So now that we have these parameters, we want to just see, okay, do they reasonably model a bulk system? So we did just some very simple tests. I won't get into too much detail. These are agricultural tests, like bulk density measurements, where you discharge into a cup and then you kind of sweep it until you get the mass and the volume, and you measure the bulk density from that. It's really a measure of the shape, how accurately you've done the shape and friction coefficient. Maybe the coefficient of restitution to a small degree. We got pretty good comparisons with that. And then an simple angle of repose kind of measurement where you discharge into a container. You get some profile, the simulations and experiment, and you use some measure of like maybe the height to the radius. Compare that, that's this first measurement, you get small error. And then we also did, we could image the surface and get the profile and compare averages from many different trials and see how closely the averages match, and doing a mean square error kind of measurement, and it also is very good.
Hello?
So it's not.
Hello? Yes.
Sorry, I don't think this lab is the host, so.
Hello?
If you're in the audience online, could you go ahead and mute yourself, please?
Mambo.
Okay, so the distraction, it's kind of hard to follow what's going on. Okay, so now that we have a DM code to take a look at the dynamics of the system, we wanted to do some damage modeling. So there are different types of damage that can occur. So compression of kernels, impacts, whether they're single or multiple impacts, and then wear. So these are the kinds of damage we looked at, and we had different tests to quantify the strength of kernels subject to these kinds of damage. So simple compression testing of individual kernels. We did some impact testing. So this is a rotary impact tester where you drop kernels one at a time. There's a blade that spins around at a certain speed. You can get the impact energy for a given kernel when it hits it. And then you collect those at the bottom and look at the damage. And then we did some pin-on-disk wear studies of kernels. What we found is that the wear was just negligible. You didn't really get much wear on corn kernels in particular, so we just didn't continue with that. Most of the damage occurred through compression and impact. And so the way we model that kind of damage is using a damage probability function, both for compression and impact damage. So the idea is this: you start with the experimental measurement. So this is like a fracture force for the compression. So you measure 100 different kernels and what their fracture forces are, and produce a cumulative distribution of that. So that's what this kind of jagged red line is. It's just the experimental distribution of the fracture force. Then we fit a curve to that. So in this case, a log normal distribution seems to do a pretty good job of describing those fracture failure forces. And then what we do at the start of the simulation, we have maybe 10,000 kernels. We assign a fracture. We choose a probability between 0 and 1 for each kernel. And let's say for one kernel, our random number comes out to be 0.6. Then we come over here and say, okay, that kernel's fracture force is now 320 newtons. And then you go on to the next one, give it a random number, maybe 0.2. That one's about 200 newtons. So every kernel has its own fracture force. And so when you look at the distribution of fracture forces in the simulation, they correspond to the experimental distribution. And we can do the same sort of thing with impact damage. So then in the simulation, as you run along, what we can do is calculate the damage parameter. In this case, we just look at what the compression force is on the kernels, compare it to our threshold for that particular kernel. And if we exceed it, then it's damaged. If we don't exceed it, it's undamaged. And one thing I should point out in these simulations is that we don't change the particle properties after the damage has occurred, but you could do that. You could say that if you could change the shape of the particles, split them in half. You could have the stiffness change because maybe there's some internal cracks, things like that. We didn't do that for the added complexity of it. And then secondly, we're only talking about a relatively small percentage of the kernels being damaged. So it probably wouldn't have a big effect on the whole bulk. Yeah.
So if the grains are not cracked, right? So how is damage affecting the simulation?
I'm sorry, the what are not?
So the clumps are not cracked, they're not being cracked, is that correct?
That's correct. So many of the, much of the damage that occurs in these kernels are chips out of the side. They're not being fragmented. They're either chips or internal cracks. Okay, so, yeah. Yeah,
So then, understood, well, it's just like a flag that mentions.
Yeah, it's a flag.
Okay.
we just tag it as this now is damaged. So for the compression damage, we looked at two models for determining whether or not a kernel was damaged through compression. One was, we just looked at the maximum force acting on that individual kernel at a given time step and saw, what's the maximum force? And if that exceeds the experimental compression force, then it's damaged. The other approach is a little bit more solid mechanics, like we basically used Mises yield criterion kind of approach, where we looked at the maximum equivalent stress during the context. So we can calculate what the volume averaged internal stress is for a kernel, and then use that to calculate a Mises equivalent stress, and then compare that to some experimental values, which we'll talk about in a moment.
What's the little F5? Yeah.
This is the force at a given for a given contact where its location is. That's what's the vector. So again, compression damage, I already described kind of the procedure for that. Just one little note. When you compress these kernels, they don't just suddenly fragment and lose all strength. So we always used the first peak. So what will happen is they'll get an internal crack, and then they'll actually gain maybe a little bit more strength, and then the fragment later. One interesting side note on this is we actually built an optical compression punch. Basically, instead of metallic platens, we changed the upper platen, well, both platens to be sapphire windows. The upper platen had a light, an LED. The bottom platen, we put a mirror under it, and then used an iPhone to videotape. So we had light transmitted through an individual kernel, and we got a video of that and recorded the sound simultaneously, so you could see internal cracks develop while you're compressing it. And interestingly, you don't always hear the crack, but you can see it in the video, a crack forming, and then they get longer, and then when it fragments, really breaks, then you can hear the crack. So that's kind of an interesting technique. So for the Mises stress calculation, we calibrated the failure Mises stress in the following way. We took our kernels and put it in that bulk compression device, looked at the kernels beforehand, made sure there were no obvious damage to the kernels, compressed it to a particular load so we can get what the average stress is in the whole assembly. And then, so then we can get a damage fraction in the experiments. And so, and then we did the same sort of thing in the simulations. And what you find in the simulations, you can get what the whole distribution of Mises stresses are in all the individual kernels. So what you're seeing here, these curves here are simulated values of the damage fraction. It's actually 1 minus the damage fraction in the kernels. So that comes from our simulations where, I'm sorry, I should re-say that. So what we did is we did the simulations where we got the distribution of Mises stresses inside the kernels. For different applied loads, the different colors are different applied loads on the top. So this is the distribution of internal Mises stresses. And then we did the experiments and got, again, for the same applied loads, at what average stress we had damage in we just achieved a certain damage fraction. And so you see that for different loads, we get about the same Mises stress at which damage occurs. Okay, so any kernels on this side would be with a higher Mises stress would be considered damaged, and any kernels to that side would be undamaged. So we calibrated what that threshold was. We validated it using what's called a Victoria mill. These are all kind of old agricultural devices that people commonly use, but basically you feed in kernels and then they go through this kind of screw. And what it does is it really compresses the material. And so we did simulations and experiments where we had nominally undamaged kernels, and then we looked at the amount of damage when they came out and tried to compare. And so what we found, first of all, in these simulations, you had to actually remove damaged particles from the simulation, because what will happen is they can get jammed into these gaps. You can see they're very small gaps.
How's that contact done with the screw?
This is a CAD file for the screw. And so you basically have a CAD file for the screw surface, a CAD file for the polyhedral particle shapes, and then the internal algorithm of the software just looks at whether there's overlap or not between the points.
Sorry to interrupt, but we have the room for another 10 minutes.
Okay, I'm getting close. So anyway, if you don't remove jammed particles, then the whole thing clogs up. In the experiment, what happens is you get fragmentation and then they just continue on, but we don't have fragmentation here. Most breakage occurs in jammed regions, so in the simulations, you can see where the damage is occurring, the locations. The experimental damage fraction was about 0.3. The DEM prediction using the max force model was about 0.2. If we use the yield stress, it was about 0.4. Not a great comparison, in my opinion. It wasn't ideal. And so we did some parametric studies and to look at some of the different effects. If you use single sphere particles, it was a terrible prediction. Everything was damaged. It was just awful. If you use glued spheres or polyhedral shapes, it worked pretty well. And actually, you didn't even have to change the shape a whole lot. You didn't, as you varied the fidelity of the shape, you got about the same results. That was interesting. If you have a larger stiffness or larger friction with the boundary, you got more damage. Larger stiffness makes sense because your stresses will vary with the stiffness. So this is a case where getting the right stiffness is important. The particle-particle coefficient of restitution, and this should have been coefficients of this particle-particle friction coefficient, and then the coefficient of restitution should have changed that. Make very little difference. Impact modeling, we can do the same kind of calibration procedure. So that's kind of a little video of what's going on with that rotary impact tester. Characterize that, again, here's the damage, the fraction of material that's damaged, and it's measured as a function of the cumulative effective impact energy. It's actually specific impact energy. So it's the impact energy divided by the kernel mass. And it's cumulative because what happens is you can get multiple impacts that grow to form some damage. And others have studied that. And there's a nice model by Fogel and Poiker back from 2003 where they used a modified, well, they used a Weibull distribution function to fit the data. And so we actually used we found a slightly modified Weibull distribution worked better. So that's what that curve is here. So many, many impacts. We get the experimental data, fit it, and now we have our damage probability function that we can use. And the way this model works is, again, you start the simulation by assigning a damage effective impact energy, cumulative impact energy for each particle from that experimental distribution. And then as the simulation occurs, you know, that kernel might impact multiple times, and you track the amount of cumulative specific energy for that particular kernel. So maybe this first impact, the cumulative specific energy is this value, but its damage threshold is there, so it's undamaged at this point. The next impact maybe adds a little more energy, still under the threshold, and then the third impact maybe exceeds the threshold. So at this point, it would be considered damaged. So you can track multiple impacts and how they accumulate before you consider something as damaged. So we did a validation simulation on that using one of these agricultural devices called a Stein breakage tester. It's just a high-speed spinning blade that lifts the particles in the air and it just beats the heck out of them. So we ran those simulations and ran the experiments and looked at the damage fraction. And you get plots that look like this. So we did this multiple times. The experimental values are the orange dots. The different plots are different amounts of material in that Stein breakage tester. And then the blue lines are the simulations from our calibrated values. And it does a pretty good job at predicting the impact damage. The kinds of damage you get to the kernels is actually up here. They start to fragment. And interestingly, it seems to be at the tips. Fragment. We also did parametric studies and found if you have more particles in there, the damage fraction goes down. And that's probably because you get some cushioning effect. Instead of hitting boundaries, you start to hit other particles. We also can take a look at where the damage is occurring around the periphery and such. And then it's interesting, you can look at the individual kernels and see where the impacts are occurring. So the plot on the left is the impact frequency, like where are all the impacts, how frequently our surface is impacted. And the right here is the impact speed or the impact energy. You get most of the energy occurring at the tips of these particles. And that's very likely because of the rotation of the kernels. And when we did spheres, we didn't see nearly as much breakage. What happens with the kernels, because of their oblong shape, they get a large rotational component. And those, when it rotates quickly, you can get a very large impact speed, and that'll occur at the tips. And that seems to be corresponding to where the breakage is occurring. So we also did parametric studies on that. Here, the elastic modulus had very little influence on the dynamics and damage. So let me talk a little bit about the kind of the grand use of all this. So we did these characterization of the corn, characterization of the damage modeling. Now let's put it into practice. So this is a model of part of a combine harvester. It's a rethresher device here. Basically, it helps separate materials and conveys the material along at the same time. So we had a big experiment where we had a hopper with material was conveyed up into a feed hopper, screw conveyed through this rethresher device, which is a series of 3 impellers counter rotating, and they lift the material up and out here. And then we sampled the material coming into the feed hopper and sampled it leaving the rethresher. So we knew how much damage was going in and how much damage was coming out, so we could look at the change in damage. So we did that experimentally and then also predicted it from our models in the computations. And we did this for a variety of conditions. By the way, this was a huge amount of material. It's like 2,500 kilograms of corn kernels. These big experiments not only require a lot of capital in the equipment, but you got to pay for a lot of material at the same time. Fortunately, being in an agricultural state, we can get corn like it's nothing, but it's a lot of material. So we ran many different trials with different feed rates, different rethresher speeds, and the results are here. It's a little hard to see, but the experimental data is the blue curves. This is the damage fraction of material for all these different tests. The orange here is from our simulation using our calibrated coefficient of restitution. And we don't get a great match. It overpredicts in the simulation how much damage we have. What we ended up doing is we artificially dropped the coefficient of restitution from a value of, we actually dropped it down to 0.55, and we got a pretty good match at that point. What we realized is the coefficient of restitution is not actually a fixed property of material, but it actually decreases with higher impact speeds. People have shown this many, many times experimentally, and especially for viscoelastic kinds of materials like corn kernels, you'll get a drop off in the coefficient of restitution speed. And so that's kind of our explanation for what's going on here, that our measured coefficient of restitution was for a relatively low impact speed. These are at much higher impact speeds. So we would effectively have a smaller coefficient of restitution. We can also look at where the damage is occurring in the device. And a lot of it, so that's where all these red dots are. And this is more of a field plot, but a lot of the damage is occurring between these first 2 impellers, as well as between the impeller and the casing. And it really makes sense when you think about this, the way these things are spinning around, that the bottom impeller throws the material off kind of up and to the right, and it hits this high-speed impeller coming the other way. So you get really large impact speeds here, as well as with the casing. So that's where most of the damage seems to occur. The company actually redesigned their rethresher based on this simulation. They wouldn't tell me how they redesigned it, but they actually made a change to minimize the damage. So it's satisfying to know that some of our work did that. All right.
So we are going to get kicked out because
I'm just going to show you pictures. We can also look at effects of moisture content. It makes a big difference in the damage models. How do you model things that aren't just kernels? I mean, so they call it material other than grain mog. When you harvest, you're taking in the stalks, the leaves, the husks, the cobs, all the stuff's going around there. They act as somewhat like cushions. How do you model all that stuff? This is coming out of the literature. it can get complicated, right? And again, you want to have fast simulations, so this is tough. How do you measure the properties? Here was an experiment where we measured the properties of corn cobs rubbing against one another. Interestingly, corn cobs have a little rough surface. If you take the kernels off, those are called bees' wings, the little bits that stand up. So you get a different friction coefficient if you do it lightly than if you compress hard, because the bees' wings collapse down. And if you rubbed it once and you come back again, you get a different friction coefficient because now they've all laid down. So getting properties is really challenging. I'll go ahead and end it there because I'm out of time, but DEM works pretty well for this stuff. It's a great application, but there's some really interesting challenges with it that there's a lot to do. So thank you. I'll go ahead and end it there.
I think we might just have to get out of the room.
I will be over in the main office in the conference room there. And I'll be around for a little bit if anyone has questions.
Yeah.
Thanks, Carl.
Thank you. All right. Thank you, everyone.
Thank you, Carl.
Yeah, it was a great meeting.
Yeah, it's good meeting you as well.
Stay in touch at some point. There are some very interesting.
Oh, okay. And by the way, I did, what, I mentioned I've seen this other stuff I did before, but I was wrong. But there's something somewhat related